Hi, I'm Professor Scott Fogler, author of The Elements of Chemical Reaction Engineering 5th edition. As mentioned in the overview, we've prepared short videos on the different parts of the text. These videos will range from 6 to 10 minutes in length. We will go chapter by chapter with these videos, hitting the salient parts of that chapter. Most of the time, we will be deriving the basic equations you will use to put in the numbers to solve problems. First, in this lecture, we're going to talk about the definitions of chemical identity, rate of reaction, and then we're going to do the general mole balance equation. We first start by chemical identity. A species is said to have reacted when it's lost its chemical identity. The identity of a chemical species is determined by the kind, the number, and the configuration of that species' atoms. A chemical species is said to have reacted when it has lost its chemical identity. There are three ways for a species to lose its chemical identity. Decomposition. Here, ethane decomposes into hydrogen and ethylene, so ethane has lost its identity. Combination. Nitrogen loses its identity when it combines with oxygen to form NO. And finally, isomerization. The number of different atoms or species don't change, but the configuration does change. Reaction rate. The reaction rate is the rate at which a species loses its chemical identity per unit volume. The convention. The rate of reaction, moles per decimeter cube second, can be expressed as either the rate of disappearance minus Ra or the rate of formation of A, Ra. The convention, consider the isomerization A goes to B. Ra is the rate of formation of species A per unit volume. Minus Ra is the rate of disappearance of species A per unit volume, and Rb is the rate of formation of species B per volume. Example, if species B is being formed at a rate of 0.2 moles per decimeter cube per second, that would be Rb is equal to 2 moles per decimeter cube per second. Then A is disappearing at the same rate. The rate of disappearance of A is 0.2 moles per decimeter cube per second. However, the rate of formation of A is going to be negative because it's not forming, but it's disappearing. CDA is not the definition of the rate of reaction as listed in some chemistry books. It simply results from a mole valence at constant volume, as we will soon see. For a catalytic reaction, we refer to minus Ra prime, which is the rate of disappearance of species A on a per mass of catalyst basis. So what can we say about the rate of reaction? We say R sub J is the rate of formation of species J per unit volume. Second thing we can say, R sub A is a function of concentration, pressure, and the type of catalyst, if any. Minus Rj is independent of the type of reaction system. It doesn't matter whether it's plug flow, batch, or continuous stirred tank reactor. R sub j is an algebraic equation, not a differential equation. Such as the rate law is an algebraic equation, for example, for the reaction A goes to B, if the reaction is first order, A disappears at a rate proportional to the concentration of A. That would be one rate law. Or rate of formation would be minus Kca. Another form of the rate law would be the rate A disappears at a rate proportional to concentration squared. That would be a second order reaction. And we'll learn about these later on. Or the rate could this form. The point is, the rate of disappearance of A is an algebraic equation, not a differential equation. So these are the four things we need to know about the rate law. Next, let's talk about the basic building block of chemical reaction engineering, the general mole balance equation. In the remainder of this lecture, we will just derive the general mole balance equation. In subsequent lectures, we will apply it to a batch reactor and the other type of reactors listed here. So the general mole balance equation. We start with the system volume. We have a certain molar flow rate of species Jn. We have a certain molar flow rate F sub j of species out. In the reactor, we generate species J at a rate G sub j. And again, our system volume is V. So we do a balance. the molar flow rate of J in, which is F sub J 0, minus the molar flow rate of J out, which is F sub J, plus the molar rate of generation of species J is equal to the accumulation. In minus out plus generation is equal accumulation. What is the rate of accumulation? Accumulation is the change in the amount of a species with respect to time. So all these have to, of course, have the same time units. Now, for a spatially uniform system where everything's the same throughout, then we know G sub J is just the rate of reaction times the volume. But if it's not spatially uniform, we have to take our system volume V and divide it up into a number of subvolumes. In these subvolumes, they're so small that the rate is uniform within these subvolumes. So we have a certain rate, delta G in subvolume 1, and delta J in subvolume 2 would just be the rate of reaction in subvolume 1, it's uniform, times subvolume 1. Similarly for subvolume 2. So if the total rate of generation is the rate of subvolume, the rates of generation in each subvolume times the corresponding subvolume. Now if we take the limit as we make the subvolume smaller and smaller, we get G sub J is the integral of R sub J to V, and then we get that the final form of our general mole balance on a system volume V is in minus out plus generation equals accumulation. And so that is essentially the end of Chapter 1, Lecture 1.